How was everyone's reading week?
Great.
Good. I have one funny story from reading week. I did something that some of you do sometimes, which is I heckled. I was at a dinner theater, and
Is that what we do?
Of all the that was the say that. And also, in saying it, you were doing it. It reminds me of a buddy of mine. This is a different story, but he saw in the bathroom once graffiti that said "bathroom graffiti is stupid," and then someone else said, "But that is bathroom graffiti," and then a third person, "Oh, that's the joke," or whatever. So anyway, I heckled. I went to a dinner theater, and one of the characters in the play was introducing the food, and his description kept getting worse and worse. I guess it was part of his character. He was like, "I have sprinkled love all over the food." He goes, "This food, it's orgasmically good." And they kept going down a particular road. Everyone around me is just like, "Oh, right." And I decided to stand up for them. So he said, "The salad, for example, I call the honeymoon salad. Do you want to know why it's called the honeymoon salad?" I was like, "No!" That was mine. Okay, so today, as you know, if you prepared for the quiz, is about scientific realism and Bayes' theorem. There's no necessary connection between the two topics. It's just sort of the last two things I wanted to cover. But before that, just a couple things I wanted to mention that I sort of missed in the last class. One thing I forgot to do was show a video, and this video I think will help you relax in graduate school. I mentioned that we talked about Loudon's idea of pursuing a research program versus accepting a research program, where accepting it means you think it's true, right? You're accepting it as true, whereas pursuing means I think there's some promise here. I'm suspending judgment on whether I think it's true, but I'm going to do research from within this perspective. And this video is from David Deutsch, someone who I've shown before. And he talks about how you can do research, and at no point does it matter whether you believe or don't believe the theory. So in that video, David Deutsch is a Popperian, so he added some ideas from Popper, but that point where he says it doesn't matter if at any point you accept or believe the theory is very in keeping with what I said about Loudon. The only other thing I wanted to add, the textbook has a good discussion of this. So Feyerabend says, given that there's no, exceptionless rule about what you should do in science, therefore, anything goes, reason plays little if any role, and that's a mistake. There are lots of areas where there are rational rules, at least rules of thumb for what to do, but they're almost never exceptionless. If you invest in the stock market, there are better and worse ways to invest in the stock market, but they are not exceptionless. Sometimes you do something perfectly reasonable given principles in economics, but you get unlucky, right? So just because there's not an absolute rule doesn't mean reason has no role to play. And as I say, the textbook has a good discussion of that. But we'll get into the meat of today's topic, which, as I say, is scientific realism and then Bayes' theorem. Someone came to my office hours and asked about this. I'll say it up front about Bayes' theorem. Please don't be scared. I think I have it in the key terms. If the terms look scary, don't be scared. We'll be going through that slowly and carefully. And I hope that at the end of today, you will have some amount of appreciation for, I think, how beautiful Bayes' theorem is. We'll see if I can succeed at getting you to like Bayes' theorem. I may not succeed with all of you, but I will do my best. So I'm going to start by actually reading the first two paragraphs of chapter 10. They're both really good at getting across the two main views, or at least the intuitions behind the two main views in this chapter. So here's the first paragraph, which is a good summary of, roughly speaking, the scientific realist's intuition. What does science try to describe? The world, of course. Which world is that? Our world. the world we all live in and interact with. Unless science has made some very surprising mistakes, we now know that the world we live in is a world of electrons, chemical elements, and RNA molecules, among other things. Was the world of 1,000 years ago a world of electrons and RNA? Yes, although nobody knew it back then. So if you are nodding and going, yes, that seems very based, then you have realist intuitions. The next paragraph captures well something like an anti-realist intuition. The concept of an electron is the product of debates and experiments that took place in a specific historical context. If someone said the word electron in 1000 CE, it would have meant nothing, or at the very least, not what it means now. So how can we say that the world of 1000 CE was a world of electrons and RNA? We cannot. We must instead regard the existence of these things as dependent on our concepts, debates, and negotiations. So again, if you're nodding along with that, then you have more of an anti-realist set of intuitions. So someone was asking about this. This is one of the questions. So we'll start off by talking about what realism means. So realism is a term that applies in many different areas of philosophy. The operative word here is real, right? So if you are a realist about a given subject matter, it means you think that claims in that subject matter correspond to something real or objectively true. So, for example, if you are a moral realist, that means you believe there is such a thing as objective right or wrong that we can know about. It's not all subjective or culturally relative. And this phrase, objectively true or objective truth, is important. So what does objective mean? Objective means something like mind independent or belief independent. In other words, if a claim is objectively true, it's true whether or not anyone believes it. Right? So if you're a scientific realist, the claim that the Earth orbits the sun is objectively true. Even when no one believed that, it was still true. Or if you're a moral realist, the claim that slavery is wrong is true whether or not people believe it. Right? So an example of something that most people would agree is not an objective truth is taste, right? Like how good things taste, right? So take the claim, chocolate ice cream tastes good. It seems like that is a claim that depends on what people think. If no one on Earth thought that chocolate ice cream tasted good, it wouldn't taste good, right? And the same is true for differences between people, right? And this is kind of an extreme example, but even something like, poop doesn't taste good, right? Exactly, right? If you do your business in the woods, you will discover that some organisms think that poop tastes good. And it's not like we're correct and they're wrong, right? Taste is in the eye of the beholder, or in the tongue of the beholder, but that sounds weird. But you get the idea. That would be an example of a truth that's not objective. So common sense realism, well, before that I'll just say one complication with this is that the world includes minds. So what do we say about that? Actually, I will say what common sense realism is. So common sense realism Godfrey Smith gives a nice definition of it that helps avoid a problem. So common sense realism is we inhabit a common reality which has a structure that exists independently of what people think and say about it. So far that's in keeping with what I've said, right? That there's truths about the world that are independent of what we think and say about it. Except insofar as reality is comprised of or is causally affected by thoughts, theories, etc. So here's a way of drawing that. So let's say, like, I don't know, this is the Milky Way. It's got like stars and stuff in it. And then somewhere is the Earth orbiting the sun. Let's say there's like a dude there, and he has beliefs, or he has a desire to throw a rock. So he thinks, I want to throw a rock. And then he grabs a rock and he throws it. So obviously, him thinking, him having beliefs and desires, etc., causes the world to change, right? He throws the rock, and that causes a change in the world. What common sense realism is saying, facts about the world are independent of what we think, except for cases like this, right? Our thoughts can affect the world in that way because we think things and then do things that change the world. But other than that, facts about the world are true or false, independently of what we think. Is that helpful? Does this make sense?
Can you describe the exception again?
So the exception is to the extent that our thoughts and beliefs affect the world in some way, right? So I think I want to raise this felt to make a point. That's a belief in my mind, and it does affect the world. But here's an example, me believing that Stevenson number XX whatever is the closest star to the sun, no, that doesn't affect the world. It's Alpha Centauri, I'm pretty sure, that is the closest star to the sun. And that's true whether or not I think something about it. So that's common sense realism. And one way of saying what scientific realism is it's just the view that science accurately describes that objective reality. That's really all that's added by saying you are a scientific realist. So scientific realism is the view that at least our best theories, maybe not all theories, but our best theories in science accurately describe the way the world is. So like that first paragraph said, right? Science speaks of electrons, gravity, RNA. Those theories are not just useful tools. They describe a mind-independent reality. So why would we believe this? So there's different considerations, but by far the most influential argument in favor of scientific realism is the no miracles argument. You could also, I guess, call it the no coincidences argument. That's really getting at the same thing, but in the literature it's called the no miracles argument. So let me build up to this. So here's something that everyone accepts, unless you're crazy. Scientific theories enable us to make predictions that get confirmed, right? Scientific theories are very empirically successful. Now, it varies from subject to subject, but just to give you an example, so there's something called the magnetic moment of the electron, which roughly, I'm not a physicist, is the magnetic field generated by its spin. So this number here, this is the predicted magnetic moment of the electron based on quantum theory. So that's the prediction that's made. Obviously, I won't test you on these numbers. You measure it, and there's an error bar here based on approximations in the theory. And then here's what you get from the measurement. And you look, ding, 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 to several decimal places, exactly right. Now that's an extreme case. I think it was Feynman who said that the predictive success of quantum physics is akin to predicting the width of North America to, I think it was within a hair's breadth was his term. So very, very accurate predictions. So everyone agrees with that. And the intuition of the no miracles argument is it would be a miracle if scientific theories could make predictions like that without being true. Right? If the theories could be that successful without being true, it would be a kind of miracle, or you could say giant unexplained coincidence. And there are no miracles, at least not in science, or you could say there are no unexplained coincidences. So we should infer that scientific theories are true, or at least approximately true. If you like deductive arguments, you can put this as a deductive argument. So premise 1 would be mature scientific theories make successful predictions and 2 is harder to write. I'll make it shorter. It would be a miracle, or you could say unexplained coincidence, if psi theories, and then basically just write 1, if scientific theories made successful predictions without being at least approximately true. So, to say that in full, it would be a miracle if mature scientific theories made successful predictions without being approximately true. Premise 3, there are no miracles. So, deductively, it follows conclusion, mature scientific theories are at least approximately true. So if you like putting it deductively, you can do it that way, but you can also just put it intuitively. So as I say, that's the no miracles argument. Any questions?
Yes, this is kind of the same thing that we talked about a few weeks ago, where it's like the darn coincidence or something.
Yeah, it's similar. So darn strange coincidence is a similar idea. Yeah, it would be a damn strange coincidence if the theory was able to lead to these predictions without being true. That's used in the context of what counts as a good test of the theory. This is applying the same kind of reasoning, but to the realism debate. Okay, I see no other hands. Now, as I say, I put it here deductively, but there's a way of putting it more in a more kind of punchy way. Now, I apologize, this video involves a bad word, but it makes the point forcefully. So cover your virgin ears, if you can't handle the bad word. Terrible, terrible.
As long as it's not a slur, I'm happy.
Yeah, exactly. I don't think it was meant in that way. But, okay, so in the same section that mentions the no miracles argument, it does mention one problem with this view that we're not going to get into in this class, although a prior class got into it a little bit. In some theories, it's not clear what it means to assert that they are true. So I gave the example of quantum mechanics, giving very precise predictions, but as we saw in a video on, I guess, the first day, it's not clear exactly what it means to say that quantum mechanics is true. It says spooky things like, an electron could be in multiple states at the same time, various other spooky things. That's not a knockdown objection against realism, but it's at least an issue they have to face. One view according to which you would not be a scientific realist is idealism. And here I don't mean idealism like being idealistic, like sticking to your ideals in a dogmatic way. I mean a view according to which all that exists are minds and their contents. So we'll see this view more in the second half of the course when we talk about philosophy of mind. So this was defended by someone named George Berkeley, who says, look, all that really exists is conscious experience. There's not a mind-independent world of matter. So simple, silly example, this blue felt, if you're Berkeley, intuitively I want to say this is an object that exists whether or not I'm looking at it. It has certain properties. Berkeley says, no, all that you have access to is I am now having a blue felt experience. And you can say nothing more than that. And then you think, well, what when I'm not looking at it? Does it cease to exist? And Berkeley, who's also known as Bishop Berkeley, then says, well, God is always looking at everything. So everything is always an experience in God's mind. So that's his way out. That's kind of a crazy view, but there are, it's easy to make fun of Berkeley on this score, but the positivists wound up saying, not that, they didn't talk about ideas being in God's mind, but they said, all we have access to is things we directly perceive. And as we saw in the section on positivism, they thought that all that science should do is talk about the relationship between observations, right? Certain experiences or observations we have may be correlated in certain ways, but we don't go beyond that to talk about the true nature of the world. Now, as we saw, positivism fell out of favor in the mid-20th century, and as a result, so I should say, the broad term for people who reject scientific realism is just scientific anti-realism. This is kind of an umbrella term that includes various views. It would technically include idealism. The positivists were scientific anti-realists. They didn't think the goal of science was to get at the objective truth about the external world. When positivism died, scientific anti-realism largely died with it. More than any other person, there was one dude who is largely responsible for resurrecting scientific anti-realism, which is Bos von Frossen. I always forget how many S's and N's there are. He has a very strangely spelled name. Let me get this right. Oh, I got it right. Okay, good. It's gotten into my head. So Bos von Frossen, who is a fellow from the Netherlands, he actually moved to Canada. I don't know if you guys know this, but one point of pride for Canada is in World War II, we took the role of liberating the Netherlands from the Nazis. We were the main country doing that. My grandpa was actually there. He missed most of the action. He came when it was mostly over. So anyone who's from the Netherlands from that period loves Canada, because we're the ones who did that. And actually did his BA at the University of Alberta, Bos von Frossen. So we get a little bit of Canadian pride for him. So there's a fancy name for von Frossen's view, which is constructive empiricism. But if it's on the test, it is. It'll just be Bos von Frossen's view. Don't worry about constructive empiricism. Godfrey Smith says, and I think this is right, it's useful to think of von Frossen as a sort of instrumentalist. So instrumentalism is a version of scientific anti-realism, according to which scientific theories are tools or instruments for making predictions. So the goal of a scientific theory is not to get at the objective truth about the world. It is to explain and predict our observations. A term that he uses is empirically adequate. So empirically meaning related to observations, and adequate meaning it explains what we see and helps us predict what we see. So example, I used this back in the positivism lecture. You think about fusion inside the sun, right? There are scientific theories about how fusion works. There are equations that say how it happens. If you're a scientific realist, you think that those equations are getting at what's really going on inside the sun. If you're von Frossen, you say, we don't know. We're going to remain agnostic about that. All we know is the theories help us explain observations. And you say, I'm not going to say anything more than that. Now, von Frossen, to be clear, he's not against theories. He doesn't think theories are bad. It's useful to think about the theory, try to extend the theory, and so on. You just shouldn't tell yourselves stories according to which these theories are getting at the objective truth. And just take my word for it, I have a video of Boss von Frossen, so we'll let him say more about his view. Okay, I'll stop it there. So you get the idea of how someone like Boss von Frossen reasons. Now, so I pointed to one issue with accepting scientific realism, which is for some strange sciences, it's not always clear what it means to believe that they are true. One issue for Boss von Frossen, that, again, this is not a knockdown argument against it, but it's a difficulty that someone like him is going to have to deal with, and the book has a good discussion of this. So we have what's observable, and what's, and here I'll erase this, and what's unobservable. So think fusion in the sun or something. And now someone like von Frossen is going to want to draw a line somewhere and say, below here, we can believe stuff. Above here, we may not believe stuff, even if the theories talk about it. What critics say is, well, this line is very arbitrary for at least two reasons. One, it's a function of our biology, right? What we happen to be able to observe is a function of how we are biologically constituted. So for example, there's a range of electromagnetic radiation, or there is if you're a scientific realist. We can only observe a narrow band of that radiation. Other animals can observe other parts. So we only believe in the narrow band. That would seem kind of strange. I mean, you could have that view, but it's at least it seems to be a rather arbitrary position. So the line is partly a function of our biology, and it's also a function of our technology, right? How good is our technology? And that, of course, moves over time. So we now have electron microscopes. Does that count as observing something or not? Well, depends how seriously you take the theories upon which it's based, I guess. As I say, I point to this not as a knockdown argument. I think Boss von Frossen, I mean, spoiler alert, I'm a scientific realist. But I think von Frossen has a defensible view, but this is an issue that someone like him has to deal with. So, well, first, any questions on our good friend von Frossen? Yes.
I'm just kind of thinking of like this as like we live in a 3D world, we can observe it, but they talk about a 4D world. Is that kind of the same thing? Like he's saying
Good.
we can't say anything about 4D because we don't experience it?
Yeah, I think someone like von Frossen is going to say what's real is the kinds of stuff that we can observe. So if you take relativity seriously, the world is a 4D space block, space-time block, I should say. That's not something we directly experience. So on a certain reading of von Frossen, you could say, well then, we would say a picture of the world according to which it's a 4D space block is useful for explaining observations, but we should remain agnostic on whether that's actually true. Any other questions about Dr. von Frossen?
What about like the moon?
The moon, I think he's going to say we can see. I mean, I've seen it many times.
What about Neptune?
We can see that.
Way.
Milky Way, yeah, we can see those. I mean, we can see them through telescopes. So then you might say, okay, is that a function of our technology?
I know, it's, yeah, I'm just what I think.
You're what I think.
It's
So
just,
I
yeah.
suspect von Frossen is not a crazy person. I think
Okay,
he,
yeah.
I think he would say that telescope counts as observation. Now, electron microscope, that's maybe a bit more
Just, is he
unclear.
still alive?
He is.
Okay.
You don't want to speak ill of the dead?
No, I was just gonna be like, man, like, you know, like if he died a while ago, it'd be like, just, you know, you could see the technology. But even then, like, just wait.
Yeah, just wait. I mean, that's because yeah, this line on a certain reading, moves with the progress of science. Okay, I'm going to go a little bit out of order. I'm going to skip ahead to the section of the book is called Under Determination and Progress, and here we're going to see a couple of the most famous and influential arguments against scientific realism, and I guess for something like von Frossen's view, or at least something in that neighborhood. The first one I'll just say very quickly. It might be later in the key terms, but under determination of theory by evidence. There should be somewhere there. So this is related to issues we saw in the chapter on induction. So for any finite set of data, right, there will be multiple, and on certain readings, maybe an infinite number of theories that are compatible with that evidence. So what that means is the evidence alone does not determine which theory you should believe in, right? So it's underdetermined in that sense, right? There are going to be multiple theories that are compatible with the data. So you have a set of data, and you want to use it to choose which theory you believe is true. Well, the evidence alone doesn't settle which theory you should believe in. So that would be a big problem for scientific realism. Now, the one that's more influential, so earlier I said that the main argument for scientific realism is the no miracles argument, right? Where given how successful science is, or at least some scientific theories are, it would be a miracle if they could be that successful without being true. The most influential argument against scientific realism is the pessimistic induction from the history of science. Pessimistic induction from the history of science.
Dude, like, who enjoys this music? You know, like, I don't.
Show of hands, anyone enjoy? Oh, okay.
I could see right when I said that, I'm like, he's dead something. I'm like, sitting there, I'm like, this is so annoying.
I'm so sorry. Said something.
Yep. I mean, I kind of zone it out because I'm, I'm teaching. But
I know. I'm like, I'm trying.
Yeah. How's everybody doing?
Great.
You can power through the music
Yeah.
if you're one of the majority. So now, in some books, it's called the pessimistic meta-induction. I think just because philosophers like to make things sound cooler than they are sometimes. We'll just say pessimistic induction. Again, pessimistic induction from the history of science. So induction means reasoning from a set of examples to a kind of general conclusion. We had a whole chapter on that. I assume you all know what pessimistic means at this point in your education. So here's the argument, and you can think of it as a direct response to the no miracles argument. There are a number of examples of successful theories in the history of science that turned out to be false. We've seen some of these, right? So there are examples of theories in the past that made successful predictions, that explained the data, etc., that had all the virtues you would want, but turned out to be false. What's one example that's come up like over and over again?
Radiology.
Maybe that.
I don't know. I'm learning
What's
about
the example in this class that we've talked about?
Einstein versus
Einstein versus Newton. So Newton's theory. So Newtonian physics explained essentially all of the data. Right? Newtonian physics was extremely successful, but it turns out to be false. So just as some examples, so one feature of Newton's theory is what's called absolute simultaneity. So if I snap my fingers, there's a slice of the universe of the moment I snap my fingers that's true across the whole universe, right? You can speak of the moment I snap my fingers, and it's simultaneous with events in galaxies far away. And so time is a series of slices like that, a series of slices in which all moments in that slice are simultaneous. In Einstein's theory, that's wrong, right? Time is relative. That's a famous implication of Einstein's theory. Another feature of Newton's theory is that gravity is an attractive force that operates instantly and at a distance. In Einstein's theory, that's false. And these are core features of Newton's theory that turn out to be false. But remember, the no miracles argument says it would be a miracle if scientific theories enabled us to make successful predictions without being true. Well, what these people say is, well, there were examples of theories in the past that made successful predictions that weren't true, like Newton's theory. Here's a simpler example that probably all of you have seen at some point, the Bohr model of the atom. You might not know that name, but this is what you see in the children's science books, or actually even high school science books. Right? There's a bunch of protons, neutrons in the middle, and the electrons are little dots that orbit in different orbitals. Right? This model enables you to make good predictions about what happens, and no one believes it. It's false. Right? It's now been superseded by quantum theory, which is too hard to teach to high school students. So we stick with this because it at least gives you a sense of what's going on. So now the induction part is, look, given that there are a bunch of examples of theories that were successful but turned out to be false, well, it's at least a reasonable inference that many of our theories are in the same boat, right? Yeah, they're helping us make successful predictions, but they're doing so without being true. Now, whether or not we accept that, does the logic of the pessimistic induction make sense? Any questions? Okay, so the view that is becoming increasingly popular in philosophy of science is one called structural realism. This is widely thought to be sort of the best of both worlds. So you'll remember that when I gave the no miracles argument, I was careful to say, it would be a miracle if the theories weren't at least approximately true. Now then the question, what does it mean approximately true? And structural realism gets more precise about what it means to say that something is approximately true.
I don't like the new sound.
Yeah.
You prefer the music?
Silent, yeah.
Oh, there we go. Well, enjoy it while it's here. Enjoy the silence. So, structural realism says that the parts of a scientific theory that we should believe are true are, there's different ways of saying it. You could say the mathematical structures, you could say the relations, or more to the point, the patterns. Right? So they'll often speak in terms of real patterns. This is a term that comes from Dennett, who will be one of the main characters in Philosophy of Mind. He's the guy with the beard who talked about deepities. So take Newton's theory as an example. So many features of Newtonian theory we know to be false, like absolute simultaneity or gravity as a force, but it gets many of the patterns right? The inverse square law, which describes the rate at which objects fall, that's still right. What you should say about Newton's theory is, if Einstein's theory is true, then Newton's theory is true in most domains. Right? Newton's theory is a good approximation of Einstein's theory, basically as long as things aren't moving too fast and gravity isn't too strong and stuff like that. But in most regimes, Newton's theory gets the patterns right, or it gets the mathematical structures right. This analogy may or may not be helpful, but I showed the duck. Well, I asked you to all look up the duck rabbit. The projector was broken. Since it was resurrected by the tech guy, the duck rabbit. To put it sort of simply, you could say that the structures, if you like, are the patterns of lines or whatever, and we can know those are real. Whether it's a duck or a rabbit is a question of the theory, and the details of the theory might change. But at least if it's a good theory, the patterns it's picking up on will survive changes between theories. So the nice selling point of structural realism is it's still supported by the no miracles argument, but it avoids getting killed by the pessimistic induction. Because we shouldn't be pessimistic, because it's the case that across theory change, the patterns tend to stay the same. So, can we apply this to psychology? So, take something like...
Isn't that a kind of similar viewpoint to Bosman and Fossen?
Good, I'm going to come back to this. So, I mean, I can answer it right now. I'll say it again later, but it is similar. There's interesting convergence between the two. Where von Frosten and a structural realist are going to part ways is unobservables. So a structural realist is going to be fine saying that fusion is a real pattern or something like that. Unobservable, who cares? It probably will survive theory change. Whereas for von Frosten, as soon as it's unobservable, well, then we just don't know. So that's the key difference. But there is I'll go ahead and read the quote. So structural realists speak in terms of, as I say, real patterns. Now, I was just curious. I haven't read all of von Frosten's book, but I skipped. If you want to know what someone really thinks, look at what they say to the best argument against their view. It's a very useful thing to do. So I looked for the section where von Frosten deals with the no miracles argument. And here's what von Frosten is forced to say. He says, any scientific theory is born into a life of fierce competition, a jungle red in tooth and claw. Only the successful theories survive, the theories which, in fact, latched onto actual regularities in nature. And that's like the most famous anti-realist, but he still speaks of actual regularities in nature, which is pretty close to structural realism. Now, they'll part ways when it comes to observable versus unobservable patterns, but this is, I think, you're right, a kind of convergence between realism and some versions of anti-realism.
In your terms, you have pessimistic versus optimistic scientific realism. Yeah.
Oh, do I have that?
Yes.
Oh. Erase it. I don't remember why I wrote that. It's not on the test.
Cool. Good to know.
I guess what I suspect that's getting at is you could be a kind of scientific realist where you say, yes, all the details of our theories are bang on, or someone who says, well, and actually Popper definitely would be a pessimistic scientific realist. There is a real world. Science at least could potentially approximate it, but we can't really know for sure whether it does. I suspect that's why I had that there, but I'm quite confident it's not on the key terms. Or not in the test.
I'm like, it's definitely on. Yeah.
Not meant to be.
Yeah.
Not meant to be. Okay, so what about psychology? Is there any application to psychology here? Yep.
Just to be clear, the real patterns are the pieces that carry through.
Yes.
Okay.
So there's different ways of saying it, but so think, for example, in Newton's theory, there's the inverse square law. It's an equation that says how fast objects fall or accelerate, on the Earth. That is still true in Einstein's theory. That's a real pattern. Now, the details of the theory about, absolute simultaneity, okay, those might change, but the patterns remain.
Bless you.
Now, what about psychology? So think, for example, about something like extroversion. So we want to ask ourselves, is extroversion real or not?
I don't know.
So what a structural realist could say is, well, we're confident it's a real pattern. So the way that we quote, discovered or extracted extroversion is factor analysis. I'm sure you've all heard of factor analysis at this point, but what you do, and obviously I'm simplifying, is you can look at the extent to which items correlate with each other and how many factors you can extract out. So when you give personality questions to people, how outgoing are you, how creative are you, how easily upset are you, and so on. There's different ways of doing it, but the consensus is the best way to do it is to get 5 factors. So 5 clumps of questions that correlate with each other, right? So the extroversion one, questions like, I like going to parties, I am outgoing, I am energetic, those tend to go together, meaning if you give a high answer to one, you tend on average to give a high answer to another. So that's a kind of real pattern in the world. And if you give scales that include these questions, the answers to those questions are correlated with behavior, right? They're correlated with things like how popular you are in school and stuff like that. So now we're tempted to ask the further question of, no, but is it really real? And what the structural realist says is, a real pattern, that's as real gets. This is the kind of thing that will likely survive future theory changes. Okay, so
It's the same thing, I know. It's just
I'll
like-
show a video. This is actually a video of a YouTube channel that we're going to see in the philosophy of mind section. It's nice. It's a podcast with two philosophers who are about as far apart as you can be. These terms, don't worry about them yet, but one of them is a panpsychist, someone who believes everything is conscious. And the other is a very hardcore materialist. It's just matter. There's no spooky consciousness stuff down there. The one with hair is the panpsychist. The guy without hair is the materialist. And they have actually a graduate student on to talk about the realism debate, and she builds up to structural realism. Although before that video, I'll actually add something here. This will annoy some of you, but there are actually two versions of scientific realism, and she has a good discussion of brief discussion of this. There's epistemic structural realism. Does anyone remember from the first day, what does epistemic or epistemology relate to? How we know stuff. So it's about knowledge. And ontic or ontological, which has to do with what's real. So there's epistemic structural realism and ontic structural realism. So here's the difference. Epistemic is the more humble position. Ontic is the more hardcore, more table-bangy type of view. Epistemic structural realists say all we can know about are the patterns. Ontic structural realists go a step further and say that's because that's all that's real. The world is patterns all the way down. It's not made of little billiard balls bouncing around. The world consists of structures and relations, nothing. Because intuitively we want to think, no, the world's made of little balls that bounce around or some kind of stuff. But if you study physics, you find that really the world isn't like that at all. And so the ontic structural realists go, it's mathematical content all the way down. So I'll show the video, and then we'll keep going from there. Okay. So if you didn't get all of that, as I say, we'll come back to those fellows in the philosophy of mind section of the course. There's another video I have here. Maybe I'll skip this one. It's in this Google Doc is in Blackboard. It's a video of John Worrell, who coined this term. He, at the end of the video, so he explains the video and some other examples from physics that motivate it. I think I've given enough physics examples. But at the end, there's a part of the video that is sort of like looking at the sun. You can do it briefly. If you do it too long, it hurts. At the end, he plays a song from his band. Kant wrote a book, Kant, famous philosopher, called The Critique of Pure Reason. Very famous and very famously difficult to read philosophy book. So John Worrell started a band called The Critique of Pure Rhythm, which that's a real funny name in philosophy. And so he plays a song that his band played about structural realism, and it's exactly as cringy as it sounds. So it's like, if you listen for like 10 seconds, it's funny. If you listen longer than that, it's just, it's too much. So you can look at that if you're so inclined. Okay, I'm gonna give another example from psychology, but any questions before I erase this stuff? Well, I guess the critique of pure reason doesn't matter. Although we will talk about Kant in a bit. All I have to say to them is, don't quit your day job.
I just wanted to be contradictory. I think I'm not.
Yeah, right after.
Okay, so think back to your intro psych courses and think about conditioning, especially classical and operant. So maybe I'll start with classical. So who's the guy who discovered classical conditioning? Okay, good. I was a little worried there for a second. Okay, good. So Pavlov discovers, so in his experiment, right, you pair a bell ringing with giving the dog food over and over again, and then you can draw a graph of how much saliva the dog releases before the food gets there, so just in response to the bell. So at first it's 0 saliva. It goes up with repeated pairings. And then after this dotted line, you stop pairing them and just ring the bell by itself over and over again. And then you get extinction. So now this pattern of acquiring an association and then losing it if you just ring the bell without the food, this is a real pattern. This is one that exists now in the cognitive paradigm, but it's conceptualized differently. The behaviorists thought of this as a kind of, and you can see this in some of Watson's writings, a kind of automatic mechanism of association, right? That's the way you get this. Whereas the cognitive people say, really what this is information transmission. Really what you're doing, and Chomsky said this in the video, is it's just a fancy way of informing the dog that bell means food is coming. And then here it kind of clues in that, oh wait, the bell doesn't mean that anymore. And there are ways of, there's some reason to take the cognitive account seriously. Like if you block awareness of it in various ways, you don't get conditioning. But the point is, however we think about this pattern, the pattern still is a real one, even in the cognitive paradigm. Now, I have a funny story. This is a little brain break about extinction. Now, in this case, it's an example of operant extinction. So, operant conditioning is conditioning that involves reward and punishment. So I have 3 younger siblings, and one great convenience of that is you have lots of stories for lectures, because you get to see psychology in action. So it's 2 brothers and 1 sister. The sister is the youngest. My parents had to try 4 times before they got a girl. And I do feel bad for her because when the 3 boys are together, like when we have a family get together, volume goes up, but IQ goes down. And this was there right from the beginning. So Nathan is the youngest brother, and when he was a baby, my other brother and I would spend time with him, and he developed the habit of hitting himself in the face. It was probably initially an accident, but then we laughed at it, which is a kind of reinforcement. And then every time he did it, we would laugh, because we like to laugh at stuff. And Nathan, even as a baby, liked to make us laugh. But my mom was a good intuitive psychologist, and she said, you guys have to stop laughing at this, because he's just going to keep hitting himself in the face. So he would hit himself in the face, and we would have to go just resist, hold back the laughter. And for a while, he was like, guys, come on, I thought we had a thing here. So extinction took some time, but eventually extinction occurred and he stopped hitting himself in the face. Yep.
The same brother that you told him he was like an old man trapped in a little
Yes.
colorful life.
Yeah, exactly. That's the, I guess, downside of having. And it's funny, like I do feel bad about how the things we did with Nathan. The sister was we never did any of that stuff with her. Like we were very protective of her. We're the kind of brothers who, if a male suitor comes over, we challenge him to an arm wrestle. We want to give him some. Look, I am a mature adult. I know my sister's going to have boyfriends, but I would like them to be a little bit scared. I think that's right. Okay, so there's a little, as I say, brain break. But as I say, the example what I'm trying to illustrate here is you can think of structural realism in connection with psychology, that the patterns survive theory change. And therefore, the patterns are what we should be most confident in. The details of any given theory, maybe we should be less confident in. So, sure, we can take a break now. We'll come back at 5, and we'll talk about metaphysical constructivism. Okay, everyone, let's keep going. So we have a bit more to cover with the scientific realism chapter, and then we'll get to the moment you've all been waiting for, some math. Please try to contain your excitement.
I'm excited, genuinely.
There you go. Awesome. So someone during the break asked me, so they had some experience doing kind of applied physics, and they said, well, who cares if the theories are true, if they work and produce the right predictions? And look, I mean, that's the attitude of a lot of scientists and certainly a lot of engineers, right? If a theory is good enough to, make predictions and help you make the machines, who cares? And look, like I talked about Newton's theory being technically false, but it's still widely used. Newton's theory, for example, is good enough to get a man on the moon. You can send a rocket to the moon using Newton's laws. You don't have to worry about Einstein. Although not so for your GPS. For your GPS, you need Einstein. One consequence I wanted to briefly mention of structural realism is you probably have to give up on the idea that you can visualize what things really exist. So certainly me when I was younger, thinking about these debates, what I wanted to do was kind of imagine zooming in on something until you get to the smallest scale and kind of visualize what an electron is or what any of these other things are. And probably that's not attainable. I think our desire for that is a consequence of the fact that we are a very visual species, we and our primate cousins, right? If we were bats doing science, we might say, I wonder what an electron sounds like. Which we, of course, instantly see that's absurd. It's a silly question to ask. But probably our desire to have a 3D picture in our head of what an electron is, probably also a kind of silly desire. If you're a structural realist and you want to know what electrons are, you look at the equations. That's what tells you what they are. Okay, so I'm going to move back a bit in order and talk about the section on metaphysical constructivism. So this is the view according to which, in some sense, we construct reality or our theories change the world. I mean, Kuhn, in his more flamboyant moods, in his more radical moods, whatever you want to call it, says things that sound like this, right? When the theory changes, the world changes. I think I made pretty clear, I think that's kind of crazy. But one way of making it a little less crazy that Godfrey Smith talks about is appealing to Kant. So Emmanuel, that's dead. Immanuel Kant, who never left his hometown, by the way. Wow. He was also very racist.
What was it?
Like even for the time, like quite racist.
What was his hometown?
Someplace in Germany. I don't think it was Germany yet. I forget, because Germany was created in the late 1800s. So yeah, I guess he wouldn't have, anyways. But as I say, on the test you'll never be asked autobiographical things. But one of Kant's famous contributions is the distinction between phenomena and the noumena. Science called the phenomenal world and the noumenal world. So, phenomena, or the phenomenal world, is the world as we experience it, or the world as we observe it. So the phenomenal world is a world of smells and colors and things like that. As we will see in the philosophy of mind section, there's very good reason to think that many features of our experience are not really features of the world. So take, color. Let me start with taste is easier. I already made some maybe ill-advised comments about taste. The fact that certain things taste good to us, that's not a feature of the object. That's a feature of us. That's a feature of how we experience it. And the same is true for color, right? The fact that this is red, what that really means is, under normal conditions, this will produce red visual experiences in humans, right? Other animals looking at this that perceive a different range of light will have different visual reactions to it. So all of that is part of the phenomena, part of the way we experience the world. The noumena is the world as it is, in itself. So when we are not looking at it, not thinking about it, how the world really is. And Kant thought there was very little you could say about the noumena. He thought that even things like the passage of time are part of the phenomena. That's a part of how we interpret or experience the world. Our mind is so constituted that we experience things in terms of time passing, but that's not a feature of the noumena. It's not a feature of the way the world is in itself. So one thing you could do to rescue metaphysical constructivism is say, well, what the theory changes is the first one. It changes how we experience the world, or the world as we interpret it, but not the noumena, not the way the world is in itself. So that's maybe less crazy. The book says that one good feature or good reminder that we get from metaphysical constructivism is that theory creation is an active process. I mean, von Frossen said a little bit in this direction in the video too. There's the positivist dream that we can just passively observe the world and chunk, chunk, chunk out come the theories. Kind of automatically. As long as we are rational and follow the rules of logic and don't postulate unverifiable things, we can just get the truth. And Popper very passionately argued against this. He has a fancy term for this, and now I'm going to forget it. But he calls it the idea that the truth is obvious, or that the truth is manifest. That you can just look, and as long as you're being honest, you will get the true theories. And he says, no, getting the right theories involves creativity, right? It's an active process. Just as an aside, this is not testable, but he said that the idea that the truth is obvious, or the truth is manifest, is a road to totalitarianism. That might seem like a strange thing to say, but what he means is, if you think the truth is obvious, and that you'll get it as long as you're being honest and rational, well then anyone who disagrees with you must be stupid or evil. Because can't you see the obvious truth? And then, well, we know what we have to do with those people who don't see the obvious truth that everyone can see. That's just a little aside, not testable. Okay, any questions on the metaphysical constructivism section and the related terms? There's one more section after this for chapter 10, and then we'll do Bayes' theorem.
What's an indifferent kind?
Yes, that's in the last one. So the last section of chapter 10 is on natural kinds and some related terms. So I'll start with natural kinds. And it's contentious actually how to define this. So how many of you have taken a class with David Wolff? So he's a philosophy prof here. Wolff, I took class, he actually wrote me a reference letter for grad school, so he's part of the reason I got into graduate school. It's a great prof if you haven't taken him. He wrote his dissertation on issues related to natural kinds. So you can write tens of pages on it. It's a very controversial topic, but roughly speaking, well, let me first give a phrase that's helpful. So there's a famous idea in philosophy of science that we want our theories to carve nature at the joints. Right? So if you're cutting an animal, the easiest way, I mean, you can get a bandsaw or something and cut through the bone, but what you want to do is carve the animal at the joints. And the idea there is the joints are sort of the natural places where you would separate things. And the idea is we want our categories, electron, gene, species, whatever, we want these categories to do the same thing. We want them to carve nature at the joints. We want them to get at the real patterns, the sort of the categories that are already there in the world. Now, that way of saying it, some people would object to, but that's what we're getting at with the idea of natural kinds. So I'll use an extreme set of cases. So on the one hand, think about a category like electron, right? That's a natural kind if there is such a thing, right? All electrons in the world, that's a category that seems to be sort of built into the world. Here's another category. My left earlobe, the Eiffel Tower, and the largest elephant in Namibia. There's a category. I just made it up. Perfectly, no one's stopping me. I can make that category. Doesn't seem like a very wise way to carve up nature. right? You get no purchase on the world by making that a category. Whereas the category all electrons, you do get a purchase on the world by dividing things up that way. I stole that from James Ladyman, but that example. Now, if you accept the idea of natural kinds, this puts you in tension with a view called nominalism. According to nominalism, all categories and concepts are made up by us, and there are no categories in the world. They're just made up by us, and the only thing that makes one concept better than another is human interests. So they would say, yeah, the concept electron is more useful than David's left earlobe, the Eiffel Tower, and the largest elephant in Namibia. It's a better concept only because it's more useful to us. But it's not like that category is in any sense built into the world. There may be some way of reconciling the idea of nominalism with the idea of natural kinds, but they are certainly in tension. So this question is pertinent to psychology, right? So suppose you provisionally accept the idea of natural kinds. Do we have them in psychology? Are concepts like schizophrenia, in some sense, there already for us to discover? Or is it kind of arbitrary where we draw the line? And here's one way of maybe operationalizing whether a concept is a natural kind. Now, it's not one you can actually use, but at least hopefully not. If everyone, or if all of civilization was destroyed and we reverted to being hunter-gatherers and had to start all over and do science and everyone, let's say, forgot all the old scientific theories and they're all burned, would we converge on the same categories later? With electron, probably yes. Schizophrenia, maybe. I mean, that's one way of posing the question. This is the kind of category we would have gotten to anyways. Two other terms, I think you asked about this. Indifferent kinds and interactive kinds. So these are different sorts of concepts or categories. I'll do an interactive first. An interactive kind or an interactive concept is one where the members of that category are affected by the categorization. So schizophrenia, definitely an example, right? The decisions we make about how to define schizophrenia make a difference to the members of that class, right? They are going to be affected by the ways we think about and define and so on schizophrenia. In different kinds, that is not true, right? You define it it doesn't make any difference to the things out there. So electron, doesn't matter what you think about electrons or how you define it, electrons are what they are. Or certainly if you're a scientific realist, they are what they are, regardless of how you categorize them. And then I believe the last term for the scientific realism chapter is eliminativism. There's actually versions of eliminativism in philosophy of mind, which we'll get at later. Basically, it's the view that a particular research area or enterprise will be improved if we get rid of a certain category. So there's a certain concept or category that is not scientifically useful, so at least that's what they would argue, and so we should get rid of it. So a perfectly defensible example that the chapter gives is the concept of race. As I'm sure all of you know, race is at best a very fuzzy concept. And if you don't believe that, the example I always give is, imagine you're in France, you take a walk, a very long walk, down to like the Middle East and then like North Africa and Sub-Saharan Africa, where's the magic line at which they stop being white, or whatever that means? And obviously, there is no such line. So considerations like that may lead people to say, okay, this is not a useful concept, we should eliminate or get rid of it. So in philosophy of mind, we'll see that some people have views like that about consciousness, or at least certain conceptions of consciousness. That they're not scientifically useful and should be gotten rid of. Now, the bald guy in the video has a view basically like that. Okay, that's the end of the scientific realism chapter. How are we doing? Ready for math? Well, it doesn't matter if you're ready or not. That's what we're doing next. Okay, so I'll start by reminding you of some things that we covered in prior chapters. So we saw back in chapter 3 that various attempts to make an inductive logic failed. Right? The positivists wanted there to be a logic according to which you could increase or decrease the probability or degree of probability of different hypotheses. Popper was, of course, very happy with that failure because he says, well, we don't need induction, we don't need probabilities, we can test theories deductively. But then the uncomfortable part of Popper's philosophy is, what do we say about, that's what we say. What do we say about theories that have survived attempts at falsification? Right? So after a theory gets tested and isn't falsified, do we give it any brownie points? Does anyone remember the term for what Popper says we should say of theories if they survive a test?
It is. Oh,
It's not O.
It's
There's a word. There's one word.
Isn't it
corroborate.
Corroboration. Yeah. So a couple people said it at the same time. So corroboration, which is pretty weak, right? All that Popper's, it's really just a word that means it has survived a risky test. Now you want to say to Popper, but can we say it's more likely, even a little bit? And he will emphatically say no, we're not allowed to say that. So Bayes' theorem is one way of being a bit more precise about what we mean when we say a theory is more likely or less likely. And I'm going to build up to it. The first key move you have to make to understand Bayesian statistics or Bayesian philosophy of science is belief should not be thought of as on or off or binary, right? People often say, do you believe this? Yes or no. The Bayesians say, thou shalt not say things like that. You should think of belief as on a range. So you can speak of degrees of belief, degrees of confidence, or the fancy term they use is credence. If someone says, what's your credence in this hypothesis? You are speaking to a Bayesian. That's how they like to talk. And so credence ranges from 0 to 1. So now you could think of it as 0 to 100%, that's the same thing, but at least in the equation it's 0 to 1. So 0 would be actually I'll do 1 first. 1 would be complete confidence that the hypothesis is true. So 100%, which you should almost never have if you're a Bayesian. So maybe something like 2 plus 2 equals 4, right? Many people would say you should have a credence 1 in that. If you're Quine, maybe 0.9999. Okay, but basically, as high as your credence can be, it should be here. Or if you're Descartes, of course, I exist. Again, should be credence 1. Credence 0, something like this, right? 2 plus 2 equals 5. Your credence should be 0 or as close to 0 as you're willing to go, right? Basically, certainty that this is false. So these should be credence 1, this should be credence 0. 0.5 would then be perfect agnosticism. If someone asks, you'll flip a coin, right? You're completely indifferent. Not indifferent like you don't care, but just the evidence is perfectly balanced. So, for example, will the Republican candidate win the election in 2028? I'm at about a 0.5, right? You know, Trump and his people are polling very low. The Democratic Party is polling very low. It's basically a coin flip who's going to win, right? So that would be an example. Now, for any empirical hypothesis, you should probably never have a credence of 1 or 0. So, for example, take the proposition the Earth is flat. So my credence in this is very low, but not 0. It's possible I've been lied to, all the pictures are fake, etc. Right? Maybe 0.001 or something, right? Very low, probably lower than that, but not 0. Something like William Shakespeare wrote the play Hamlet, maybe 0.9. There's some fringe people who argue someone else wrote it. It's possible, but I would have a pretty high credence in a claim like that.
What about, that humans have been on the moon?
0.995, probably
Oh, okay.
higher. Yeah, very high. I mean, some of you may not agree with that, but
I was like,
well, actually, I have a funny story about
I
that.
believe that, but like my boyfriend and his sister, they're like.
So when I lived in Alberta,
In Alberta.
Yeah, I lived in Alberta. So I dated this girl who's from a small town with 10 people, not 10 people, but not very many. We were watching a TV show, and someone made a joke about us not landing on the moon. And I was like, do you know anyone who believes that? And she's like, do I know anyone who believes it's real? In which case the answer is no. I was like, oh, okay.
Yeah.
It's a very different conversation.
In Alberta.
In Alberta.
In Alberta. Yes.
Yeah.
Rural Alberta.
Rural Alberta.
I don't know. It's very weird.
So anyway, now I'm not.
It's a
This is
totally
not,
different world.
It is a different world. So now this is not a class about astronomy, although at some moments it may have felt
Hey,
like that.
I mean-
But, so anyways, does the concept of degrees of belief or a range of belief make sense so far? Yes.
Yes.
So as I say, my goal here is to go slowly.
Slow.
Now, you may want to, and many people do say this, object and say, yeah, fine, I have kind of a rough sense of what you're getting at, but can we be more precise about what it means to assign numbers? Because some would say, you just pulled these numbers out of the air. And I mean, I did. Can we be more precise? And the way that Bayesians try to be more precise is in terms of betting behavior. They say that we should think of these numbers as relating to what kinds of bets you would make. Now you have to assume a few things, like for example, that people like making money. If you assume things like that, you can, as I say, make this more precise. So here's an example. Here's a sentence. There will be commercial space travel within 10 years. So meaning you'll be able to pay a lot of money to take a rocket up to the station or the moon or something, in space. So how likely is that? And you might think, I don't know, boy, how do you give a number to how confident you are? Well, here's a simple way you can do it. You show people a picture like this, or a real object like this, where there are 4 balls, 3 of which are white and 1 of them is black. And you say, you can take one of 2 bets. You can take commercial space travel will be available in 10 years or less. Or in 10 years, I will come to you with this thing of balls and I will pick one out. And if it's the black one, you get the money. Which bet do you want to take? If you want to take this one, it means your credence in this is lower than 0.25, right? Because here we know the probability is 0.25, if the guy's honest, that you'll get the black ball. And so if you would rather take this than this bet, then your credence in this is lower than 0.25. And then you just keep expanding it. So you might make it 9 balls, 1 of which is black. And you say, how about this? Would you rather take this bet or the space bet? Yes?
What if you don't care about space travel and you just want the money either way? So
Oh, it doesn't matter. It doesn't matter if you care. It's just about how confident you are. So it's not that you'll get a free trip. It's just okay, I'll pretend I'm actually doing
It doesn't
this.
mean I'm confident in gambling either, but I'd rather have money than. So in my mind, it's not about which one I'm confident about. It's about I don't care. about the space.
It is about what you're confident about in the following way. So like, if you care about money, so let's say you really want the $100, and I come to you and say you have two choices. You can take this bet where if there's commercial space travel in 10 years, you get $100.
Oh, I get money for it. either
Yes,
way. Oh.
exactly. Yeah, so
I
it's
thought it was just like space travel or money. I'm like, well, I'm gonna take.
No, good. I'm glad you clarified.
Okay.
So it's either way you get money. Don't worry, you're all
Okay.
getting money. This imaginary thing I'm not going to do.
Okay. Okay, then
so-
you can ignore what I said.
Yeah, well, no, it's good. It's good to clarify. I'm sure you weren't the only ones. It's good to clarify. So now in this case, if it's this or this, I'm not sure which bet I want to take. If you're at the point where they seem kind of equally good bets, that's roughly what your credence is. So in this case, my credence is a little over 10% that this will be a thing, roughly. So that's one way of making this a bit more precise. Okay. Does that any other questions? Okay, so now I will actually write out Bayes' theorem, and we'll go through it. So there are two versions of Bayes' theorem. I'll actually start with the longer one. Believe it or not, the longer one is actually more helpful, I think. So on the left-hand side is probability. I can tell this part is on its last legs. Let's try green. The probability of the hypothesis given the evidence. So the straight line means given or in light of. So how likely is the hypothesis given the new evidence we see? So we have a hypothesis, we have some new evidence that comes in. Should this evidence cause the probability of the hypothesis to go up or down? And probability here, what I mean is, at least in this context, how much you would bet on it, or how confident you are in this hypothesis. All right, like what we've been talking about, right? Degree of belief or credence. So how do we figure out what this is? So the top part is probability of the evidence given the hypothesis, so it's the reverse, multiplied by probability of the hypothesis. So let's break these down. This one is called the prior probability, the one that just says PH. So this is how confident you are in the hypothesis before you look at the new evidence. Another way of saying this is, how confident are you in this hypothesis based on your background knowledge, based on what you already know? I mean, an example I'm going to use later, let's say that the hypothesis is aliens have visited Earth, and the new evidence is a particular flash of light in the sky. So now before you even look at this new evidence, you have some prior, right? So if you're like me, your prior is very low, that it's aliens, right? Given what my background knowledge and beliefs, I need a lot of convincing before I think it's aliens. Some of you may have a higher prior, but as I say, this is not a class to convince you of things like that, but you have some prior before you even look at the new evidence. This is, if the hypothesis was true, which we don't know if it's true or not, but if it was true, how likely is it we would see this evidence? So if aliens really did visit Earth, how likely is it they leave a flash behind? It's not that unlikely. So probability of the evidence given the hypothesis. So this is the top part is then divided by the first half of the bottom part is just this again. So that's easy. Okay, so I'll put square brackets just to emphasize this is a separate thing. Now we have this again, but with noughts added. So plus probability of the evidence given naught. That's how logicians write naught. You can write the word naught. What's in the key terms? Does it say naught or
It says not.
It says naught, so that's fine too. given naught multiplied by probability of not hypothesis. Square brackets aren't strictly necessary, but they make it clear. When I taught this at the U of A, I accidentally wrote a plus here. Very embarrassing. So the plus is here. This is supposed to be a plus, the rest are x's. So what this is getting at is, how likely is it we would see this evidence if the hypothesis isn't true? So if there's not aliens, how likely is it there'd be a flash of light in the sky? That's actually, it happens all the time, right? So it's not that unlikely. And this is the prior probability of not the hypothesis. Yep.
Where did you get this number for your, for example, the probability based on your prior experience?
Good question. You basically make it up. Although I should add to that, I'm going to say this later, but this, the next time you do a study, will become this. So this is called the, and I'm getting ahead of myself just to answer this question, but this is called the posterior probability. So it's the probability after you see some new evidence. A good Bayesian mantra: today's posteriors are tomorrow's priors. So the next time you do it, this number will go here. So that makes it a bit more rigorous, but let's say the first time you do some test, you basically make this up.
Just anything.
There's no strict rule for what this has to be. So that's kind of, this is the weakness. This is the kryptonite of Bayesian reasoning. Is you can, there's no rule that says what your priors have to be.
So it kind of like improve your things like.
Exactly. The hope is, even if you have a silly prior, if you do enough tests, you'll get closer to the truth. Would be the hope. Yeah.
Would that be the degree of belief?
It's the degree of belief at the beginning of before you look at the evidence. This is the degree of belief after you look at the evidence.
Okay. Yeah, so it really is just like an arbitrary, be like, yeah, I could see that. So you
Yes.
say whatever. Okay.
Exactly. Yeah. And like I said, the hope is that if you do this enough times, if your prior is silly, over time it'll adjust in light of the new evidence. Now, one way to think about this is it's really x over x plus y, right? Because this is here twice, right? This chunk, and then there's this chunk. So it depends on what the hypothesis is, but let's say you want your hypothesis to be true. You want this number to get closer to 1, the result of this. And there's two ways to get it closer to 1. For x to be bigger or y to be smaller, right? So if the evidence is really likely in light of the hypothesis, or your prior is just really high, this will make the x part bigger, and then it'll be closer to 1. Or, so this part's y. If it's just very unlikely that you would see this evidence if the hypothesis weren't true, that will make this part smaller, and then the overall thing will be closer to 1. Quick thing, and this is the only part where this is true. These two have to add up to 1. The probability of H and the probability of not H, those have to add up to 1. Okay, now we're going to do a real example, although, that makes me sad. When I did this last time, I had more room on the board.
You could put up the thing and.
I could. That's out of the video. For the future generations of 3309. Here's what I'm doing. I'm going to kill this part. Or here, I'll write it here. Probably with H given E. So I have in front of me 2 piles or heaps of pens. So we'll call this heap 1. It has 3 blue pens and 1 black pen. So heap 1, 3 blue, 1 black. And this is the heap I will take something from if I flip heads. The other one, which I will draw from if I flip tails, which we'll call heap 2, has only one blue, and you guessed it, 3 black heads. Okay, so you all can observe I am telling the truth. So I will put these out of sight over here. And then I will flip a coin. So again, if I flip heads, I will take a pen randomly while closing my eyes from heap 1. If I flip tails, I will take it from heap 2. Okay. Okay. This is what I picked up. I picked up a black pen. Now, which heap did I draw from? Which did I flip? So you should not have 0 or 1, you should have some level of credence. And this will tell us what our confidence should be. So let's say it's the probability of heads. We'll do heads because then it's H. See, isn't that nice? So what's the probability of heads given what I just did? So what's the evidence? Black pen. The hypothesis is heads. So let's start with the prior. What is the prior? Before you look at the evidence, what's the probability I flipped heads?
0.5.
0.5. See, this isn't so bad. What's the probability? Now the evidence is black felt. If I drew from heap 1, what's the probability of seeing black pen? 0.25. Now, all this just gets reproduced right here. 0.25 times 0.5. Okay, now, if the hypothesis is false, what's the probability of seeing the black pen? So if it's actually heap 2, what's the probability of getting the black pen? 0.75. And then what's the probability of the not hypothesis, the probability of tails? 0.5, see? So now you have all the ingredients you need to calculate the probability. You guys have phones? Calculate. I'll give you 10% bonus. No, not actually.
Yeah, but that's a lot of effort.
Okay, has anyone got it? Someone say it out loud. Good, 0.25, good. So in this case, it's very clean. It's not always going to be this clean, but I deliberately made an example that's, kind of easy on the old head. But yeah, so that's how you do it. Now, this is a simple example because we know the quantities involved. I'm going to use now a different example that's more akin to theory testing. But first of
was it heads or tails?
it was tails.
Okay.
So you had a low probability, actually. It was false. It was tails. So let's do a different one. Let's go back to my alien example. So the hypothesis is aliens visited. And the evidence is a streak of light at night. Okay, so I'll erase these. So probability of E given H will actually be reasonably high. So often people with, no offense, crazy views will focus on this while ignoring the rest. It's not like they're doing Bayes' theorem in their head, but they'll say, well, if aliens did visit, there would be a streak of light. And that's actually pretty reasonable. So this might be something like 0.8. I guess maybe the aliens have cloaking technology or something. But if there was an alien visitation, it's reasonably likely there'd be something like a streak of light in the sky. So now here, as I already mentioned, the prior probability will somewhat depend on your prior beliefs and background knowledge. In my opinion, should be very low. So your confidence in the hypothesis that aliens visited, at least mine, given my background knowledge, is pretty low. And then again, you just reproduce it here. 0.8, 0.001. Now, this is often very important. This is how likely is it we would see a streak of light if there weren't aliens? Now, it doesn't happen every night, so I don't know, you could debate, maybe 0.5, probably not as high as this, but it's not that unusual for there to be some kind of streak in the sky at night. And then this just has to be this minus 1, or 1 minus that, so 0.999, yeah, whatever. So I'm not going to make you do the math for this one, but it's going to be low, right? Given how low the prior is, the result of this will be a small number. Oh, I just realized there's an entire activity I forgot to make us do.
What?
We can do it now. So I was supposed to do this before Bayes' theorem, but that's okay. We will do it now. This may be actually somewhat fun. So, in fact, I'm going to post this on Blackboard. So open up Blackboard. So here's the way it works. There are a set of statements here, and try to do them on the quick side. What you have to do for each is say whether you think they are true or false, and then how confident you are. And just pick one of the 5 options. So 55% means you really have no idea. You just you have a slight gut inclination one way, but you're basically guessing. And then 95% is you're very, very sure that this is, in whichever answer you gave, true or false. So that's part 1. So at least get started on that, and I'll explain the next part. Okay, just for the sake of time, I'm going to explain what the next step is. So you can finish like after class or later if you're so interested. But what you're going to wind up doing is at the very bottom of the page, which you should not scroll to. So right below so there's 40 of them. Here you're fine. Here you're safe. Well, I guess at the end you'll scroll down to the bottom and mark yourself, like how many you got right. Mm-hmm. And then just look at all the ones where you said you're 55% sure. How many times were you right? How many times are you wrong? And then what percentage of the time are you right? So A divided by A plus B. So this divided by the total. So on for the other ones. And then what you do is you plot your scores here. So the x-axis is how sure you were. And then the y-axis is how often were you right. And if you're well calibrated, the dots should be close to the line. So if the dots are all perfectly on the line, that means when you are roughly 50%, 55% sure, you get it right around 55% of the time. When you're 95% sure, you get it right around 95% of the time. So it's an interesting activity to see, I guess, how well calibrated are your degrees of confidence. But as I say, for the sake of time, I do want to finish the rest of the material. So there's a section in the book on the subjectivist interpretation of probability. So the idea here is that, what are these P things? When we say, probability X, when we're testing a theory, what is that? And most philosophers who work in this area say that these are states of a subject. It's how confident I am in the hypothesis, or how much, what kinds of bets I would make about this hypothesis. And this theorem, Bayes' theorem, follows from a very simple set of assumptions. And the assumptions, or a reason to take the assumptions seriously, is something the textbook calls a Dutch book situation. Which is a fancy way of saying, if there's a set of probabilities you have, that, so for example, one assumption that you need to get Bayes' theorem is that mutually exclusive probabilities should add up to 1, right? So for example, you shouldn't say I have a 75% confidence that the coin will come up tails and a 75% probability that it'll come up heads. That's a Dutch book. It's a case where your bets or probabilities violate the assumptions of probability theory. And the basic truth is, if you have a Dutch book, if you have bet-making behavior that violates the assumptions of probability, you are guaranteed to lose money, right? If you make bets in accordance with that, so that, the way it works is, right, you make something like 3-to-1 odds. If you make a 3-to-1 odds bet, that means you're 75% confident in something. And so, if you get it right, you get $20. If you get it wrong, you pay $60. Something like that, right? So if you're betting like that, and you violate the rules of probability theory, you're guaranteed to lose money. That's what the Dutch book is about. Now, probability theory can't tell you what your priors should be. Right, so someone asked about this. This you basically make up, at least when you start your investigations. But what probability theory tells you how to do is how to keep your probabilities consistent, right? So that you're not contradicting yourself or putting yourself in a situation where you're guaranteed to lose money. Okay, I'm going to show a video giving some other examples of Bayes' theorem. I believe this one uses examples from medicine, but it uses the short version of Bayes' theorem. The short version of Bayes' theorem, oh, and by the way, free gift, someone asked about this in office hours. One of the items in the test will be the long version of Bayes' theorem. So that's for free, so just memorize it.
What do you mean, like we have to write it?
You have to write this,
Formula?
the formula.
So it'll just say long version.
It'll just say Bayes' theorem long version.
And then we
Yep.
just have to.
And we just have to write that, okay.
Oh, you're
Yeah.
already answered it.
Yeah, so it's in the key terms. Now, you could just memorize it through brute force. I strongly recommend understanding the ingredients. That will probably make it easier than memorizing every letter.
What if I get a tattoo on me?
Honestly, I would be like kind of impressed. I kind of be okay with that.
Holy Sparks.
Yeah, that's right. Although it could be a temporary tattoo. Then that's, I feel like I should be less impressed by that.
That's probably be cheaper for me.
I guess I can't actually accept this because then I'm in
Right?
yeah, did you say that there's trouble finding
It's
it?
not to go through the trouble of finding a temporary
have to-
tattoo of Bayes' theorem.
Oh, I guess so, yeah.
Custom made.
I thought you meant finding it on, like, depending where you put it, that would be an issue.
Oh, that would also be an issue. Yeah.
But anyways, so the short version of Bayes' theorem, the bottom just has probability of the evidence.
Yeah.
And the way to think about that is, look at the two parts of the bottom. Part of it is, how likely is it we would see this evidence if the hypothesis was true, and how likely is it we would see the evidence if the hypothesis is false. So this is mathematically equivalent, is just, well, how likely are we to see the evidence in general, right? So that's mathematically equivalent. So I'll show a video that gives some more examples, and I believe it uses the short version. I'll stop there. So that's a really helpful example. There's a saying, I think it's a saying in medicine, that when you hear hoofbeats, think of horses, not zebras, right? So, at least if you're in North America. So that's, again, getting at the idea of the prior probability, right? The prior probability that the hoofbeats are caused by a zebra around here is very low. Maybe escape from the zoo, but it's very low. You go to the doctor, like in this example, and you say, Doc, I'm coughing, I have pain in my chest, my throat is sore, some random, rare, deadly disease. I'd be very likely to get those symptoms if I had the crazy disease, but the prior that you have it is very low. So most doctors will just say, it's probably the flu, right? So that's another nice example. So as I mentioned during the video, because I didn't want to add confusion, I'm not going to ask you about the term conditional probability, but what I will ask you to know is these two. So probability of E given H and E given not H, those are called the likelihoods. So that's the probability of seeing evidence given the hypothesis or not the hypothesis. And look, those also, at least in most realistic cases, are somewhat made up. So think about the theory of evolution. And let's say the new piece of evidence is you find Lucy, right, the fossil of the Australopithecus. How likely is it we would see Lucy if evolutionary theory is true? That number also is kind of made up, at least in realistic cases like that. I mean, in my pen case, it's well defined, but in the evolution case, not so well defined. So the book talks about how there are models and theorems where you can show that two people who have different priors will converge given enough evidence, but often those models assume things like they have the same likelihoods, so the same subjective probability of how likely it is we would see this evidence given the hypothesis. And that's maybe a generous assumption. So I was going to talk a bit about ways of connecting this with Popper and confirmation and disconfirmation. I might just skip over that. I mean, just very briefly, one option that many people take is you can just say, forget about Popper, forget about deduction. We should use Bayes' theorem both for confirmation and disconfirmation. It's more realistic. It cashes things out in terms of probabilities. Another option is you could say, I'm with Popper on falsification, because that you can do deductively, at least if you idealize a little bit. So falsification still has that. But when I'm talking about a theory being confirmed or supported, then I'll use Bayes for that. And actually, Lakatos, I discovered this recently. A former student of mine was reading Lakatos, and he recommended this book to me. He has a passage, section of a chapter called A Plea to Popper for a Whiff of Inductivism. Basically saying, please Popper, add a little bit of probability or support to your ideas. And Bayes' theorem would be maybe one way of doing that. I could say more there, but that's probably good enough. What I will do, though, is add some connections with psychology. One other thing I will add that connects to a prior chapter. So someone asked about damn strange coincidence earlier. So now I've erased it, but right here was probability of evidence given not hypothesis. So how likely is it we would see this evidence if the hypothesis is false? This is one way of quantifying the idea that something is a damn strange coincidence. One way of saying that is, it's very unlikely we would see the evidence if the hypothesis is false. So I think the example I gave in a prior chapter was, suppose I have a theory and it enables me to predict exactly on what days it will rain, and I get it right, that's the evidence. It's very unlikely I would be able to do that if my theory is wrong. Right? So that's one connection. Now I'll close us off with 3 points of connection with psychology, since this course is called Critical Issues in Psychology. Although, I could save those for test review day. Show of hands, who would rather I save that for test review day?
I don't know what the other option is, though.
A slight majority. So here's what I'll do, actually. Those I will save for test review day. Don't be that happy, no. But what I will say a few things just to wrap us up. I'll in fact give you a gift, which is I'll tell you what the 2 written will be. So next class is, as I say, test review day. So I would strongly recommend that you test yourself on the key terms before then. Last time there was only like 20-30 minutes of questions, but given the range on the test, some of you could have asked more questions. So I would recommend coming with questions ready. As I say, I'll start the class off by finishing up some connections between Bayes' theorem and psychology. The 2 written questions are the following. One will be explain what must occur before a scientific revolution takes place, according to Kuhn. There are 2 criteria. Please illustrate this with an example, either from the book or lecture.
Do you have this on Blackboard?
No. So what's on Blackboard is the essay. So this is in 2 weeks, so you don't have to worry too much about this, but the first half of the test is the same format as test 1, 15 definition, 2 written, one of which will be the Kuhn question I just said. And then there'll be the in-class essay, will be the second half, and that's on Blackboard. The in-class essay is the Popper versus Kuhn stuff.
So can you repeat that? Explain what must occur before a scientific revolution occurs.
Yeah, so explain what must occur before a scientific revolution according to Kuhn. So there's 2 things that have to happen, and give an example either from lecture or from the book.
One example or 2?
Well, one example that illustrates both, if that makes sense. So like an example that you then connect with, like one example of a scientific revolution. You could look hard to find one outside of lecture in the book, but that's safer probably.
Probably, yeah.
Go with that. The other written will be explain one argument for scientific realism and one argument against. There's a pretty obvious choice. There are multiple options, but there's the 2 that are sort of the most straightforward to pick. And the essay you already know about. So I will stick around if you have questions, but you're free to go. I'll wrap up the base stuff at the beginning of test review day. See you all then. Yep.
Can you define convergence?
Sure. Oh yeah. So, well, convergence I did talk about. That's the idea that, at least if you idealize, 2 people that start out with different beliefs, if they get enough evidence, converge on similar beliefs. If they use base theorem.
Oh, okay.